performed for a few operating conditions. Now, in the next step, we usually develop the model and we validate our model using those experimental data available at limited operating condition. Then after validation, confidently we can extend the application of our model for other operating conditions at which experimentation is not done so far. This is the first point. Second point, I told to train the operating personnel. Along with the startup condition, shutdown or normal condition, we also need to have some experience about the plant behavior at abnormal situations. So we can run our simulated model and we can observe what is happening at abnormal situations. So this is regarding the second point. And third point, selection of controlled variable, manipulated variable pair. Although we have discussed this with our physical understanding of the process, but there are certain criteria based on which usually we select the controlled variable, manipulated variable pairing. And for that we need the process model. I also mentioned that this is beyond the scope of this undergraduate course and it is taught in master's level under advanced process control course. The process model is also required for controller tuning. This we will study in this course for controller tuning. Fourth one is model-based controller development involves the model. The name itself suggests that this model-based controller requires the process model. And last one is the for finding the optimal operating condition, we need to use the process model. Right? These are the five important points related to the necessity of simulated model. Okay, so next come to this topic, state variable and state equation. Let us first discuss state variable. You can note down these points one by one, and I hope you can understand these points easily. State variables are used to describe the natural state of a process. State variables are used to describe the natural state of a real life process. There are three fundamental quantities: mass, energy, and momentum. There are three fundamental quantities: mass, energy, and momentum. But point is that these three fundamental quantities are not directly measurable in industrial practice. These three fundamental quantities are not really measurable for a particular process. One example is given, like mass. Mass we cannot directly measure. So how you measure this mass? First we need to know, suppose if we consider a liquid tank system, first we need to know the cross section of that liquid tank. Then we need to know the liquid height along with density. I repeat, the mass we cannot directly measure. for a process. So how we proceed? First, we need to know the cross-sectional area, capital A. We need to know the liquid height in the tank, H, along with density, rho. Now multiplying these three, we can calculate the mass. Directly, we cannot have the information of mass. Now, if we want to calculate this mass using this AH rho, you see A and rho, they are constant quantities. So only variable is here height, liquid height in the tank. Fine. So this height is used to basically characterize the mass, and height is the state variable. I repeat, for calculating the mass, we need to know cross-sectional area A, liquid height H, and density rho. Among these three, area A and density rho are constant quantities. Only variable involved here is the liquid height H. So this height is the state variable, which is used to characterize the mass. In this fashion, there are several other variables I have mentioned here. You see temperature, pressure, concentration. Rho I have included here. It is, if rho is a variable, in that case rho can be included here. Otherwise, these three you can consider, which are widely used for chemical processes: temperature, pressure, and concentration. Fine. So these variables, temperature, pressure, concentration, are used to calculate the mass, energy, and momentum. So in gist, I can tell that state variables are usually used to characterize a natural state of a process. State variables are used to describe the natural state of a process. There are three fundamental quantities: mass, energy, and momentum. And these three fundamental quantities are not directly measurable in industrial practice. So to measure the mass, energy, and momentum, we need to know some basic variables like temperature, pressure, concentration. And these characterizing variables are called state variables. Okay. Now you can note down one important point related to this state variable. State variable is usually present in accumulation term. Note down this point. State variable is usually present in the accumulation term. I will show you how it is involved in the accumulation term. State variable is usually present within the accumulation term. So this is the easy way to identify the state variable in an equation, in a modeling equation. I'll discuss this issue again. Let us finish this topic. State equation. You note down this definition. Note down this definition for state equation. See, this state equation is nothing but the conservation of mass, conservation of energy, and conservation of momentum based modeling equations. State equation is nothing but the equation which is derived by the application of either conservation of mass or conservation of energy or conservation of momentum. This is a state equation. Straightforward way to remember this. For a particular process, if you apply the conservation of mass principle, and if you get one equation, that resulting equation is called state equation. Fine. Now let us take one simple example to understand this. I think you know this conservation principle. It is written in generalized form. This is the conservation law. In generalized form. You see, rate of accumulation equal to rate of input minus rate of output plus rate of generation minus rate of depletion. So what do you think? We will keep the rate of generation, rate of depletion both, or what we can do related to this? Anyone can give the answer. My question is, in this generalized equation, we need to keep both the last two terms, or we can do something.
So we can replace it with a single term called rate of change of the quantity. So it can be either positive or negative to show whether it's generation or depletion.
So basically they are identical, just they differ with the sign. Okay. So either we can put here rate of generation or rate of depletion. Fine. Suppose we are keeping here rate of generation. If depletion is there, you just change the sign, minus rate of generation. This is the way. I repeat, we can keep either rate of generation or rate of depletion. Suppose we are keeping rate of generation, but originally in the process rate of depletion is occurring. In that case, you just change the plus sign and write minus rate of generation. Anyway, I think we'll consider this with an example, so there will not be problem to understand it. Now, this statement I think well known to everyone. Total mass cannot be generated or depleted. So there is no generation or depletion term in total mass balance equation. There is no generation or depletion term for total mass balance equation. But if we consider component mass balance, they will be there, which is shown here, you see. So mass balance equation we use in two ways. One is total mass balance and then component mass balance. For total mass balance, there is no generation or depletion term, but for component mass balance, it is there. You see, I have written only one, rate of generation. But if you see rate of depletion is occurring, you just change this term to minus rate of generation. That's what I wanted to say. Fine. In the similar way, we can write the energy balance equation. Rate of energy accumulation, rate of energy input minus output plus rate of energy generation. what I told, within this left hand term, one variable is present. That is state variable. As mentioned previously, one variable is present within this accumulation term that is identified as state variable. Okay. And one thing I want to mention here, usually in case of process control course, the momentum balance equation is very, very rare. Okay. Momentum balance equation is very rare. They are specific to fluid systems, etc. And they are very uncommon for process control study. Now let us come to one example. You see, this is a liquid tank system. You draw this figure, open loop process diagram. Fine. So this is the liquid tank system, and this is the mass balance equation. Nitin Baghel 10027. Nitin Baghel 10027. Soeb Nazir 10060. Soeb Nazir 10060. Udaya Misra 10063. Udaya Misra 10063. Utkarsh 10064. Utkarsh Singh 10064. Bhirabomma Sai Venkat 10065. 10066. Chinmay Jain. Akhil Nama 10076. Akhil Nama. Rohit Dhamija 30015. What happened today? I'm not getting any response. Anyone can tell this is, what is ape? Can you tell me?
Sir, volumetric.
Volume flow rate.
Volumetric flow rate, correct. So I think you understood this equation, no? How we get area and H, this is volume. Volume into rho, this is mass. So dm dt basically this one. Fine. This is also mass flow rate. This is mass flow rate. So from this mass flow rate, we can get this equation with the assumption that rho is constant. If rho is constant, we have this equation. Now, which variable present in the accumulation term in this equation? Which variable present in the accumulation term?
Sir, height.
Fi.
Height. Yes. You see, in the left hand side, we have the term rate of accumulation. It may be mass or energy. Fine. So this is our left hand term. So in this left hand term, this area is definitely constant. So we are not considering this. So within this term, dH dt, H is our variable. So H is identified as state variable. It's very easy to identify. Fine. And this equation we obtained by the application of conservation of mass. Therefore, this is state equation. This modeling equation A dH dt equal to Fi minus F naught we obtained by the application of conservation of mass. Therefore, this is state equation. So I hope there is no confusion to understand these two topics, state equation and state variable. Clear? We got this state equation by the application of conservation of mass. That's why it is called so. And state variable is present within the accumulation term, which is very obvious from this equation, you see. If you have any doubt, you can ask me on these topics. No doubt? Okay. Then let us come to our next topic. Degrees of freedom. Our next topic is degrees of freedom. Now here degrees of freedom we are denoting by small f. Degrees of freedom we are denoting by small f, and this small f equal to v minus e. V represents the variables and capital E represents the equations. Okay. This capital V represents the total number of process variables which are independent to each other. You remember this, total number of process variables which are independent to each other. And E is total number of equations. So why I have added that independent to each other? Anyone can give any answer or example in support of this additional statement? Total number of process variables that are independent to each other. Any example? Yes.
Sir, like mass and volume are two independent variables, but if we consider density, so like it depends on mass and volume. So like it cannot be considered as an independent variable.
It is somewhat like this, according to your example. Suppose in the last example, liquid tank system, you see volume is equal to area into height. Fine. So either you consider volume or height within V. You cannot consider both. Got the point? I repeat, let us consider the last liquid tank example. In that example, volume is equal to cross-sectional area into height. Cross-sectional area is constant. So either you consider volume or height as a process variable. You cannot consider both. That's what I wanted to say. Fine. And second one is total number of equation. Now let us consider a couple of cases. There are total 3 cases. You see, in case 1, f is equal to 0. Our degrees of freedom is equal to 0. That means number of process variables equal to number of equations. I can say in a little different way, number of unknown process variables equal to number of available equations. V equal to E. That means number of unknown process variables equal to number of available equations. So this type of system is called exactly specified system. This system is exactly specified if V equal to E. Okay, but in this case we may not have unique solution, particularly for the nonlinear equations. Now our second case, which is quite common, that is f is greater than 0. It means number of unknown variables is greater than number of available equations. And these type of systems are called underspecified system, which are quite common. Now, you know, at the end of the day, we need to do f equal to 0. Now, question is how you can do that. If f is greater than 0, in this case, we need to transform the system to f equal to 0 or specified system. Now, question is how to make it. We are coming to this point. Let us finish another case, that is f is less than 0. That means number of available equations are more than the number of unknown variables. Number of available equations are more than the number of variables. These types of systems are called overspecified systems. It is quite uncommon. Okay. This is quite uncommon. Now let us come back to our this question, green color question. You see how to make it exactly specified. First case is fine, f equal to 0. So there is no need to do any additional work. Now case 2 is quite common, so we need to discuss this issue. Okay. Now question remains there, how to make it exactly specified. Anyone, any answers?
So we have to introduce more equations.
Good. What's your number?
So 19CH 30024.
Yeah. Any more addition to the answer? One answer we got, that is yes.
We can identify the variables which we can directly measure.
I mean, you want to say that we can measure more number of variables so that we can reduce the number of unknown variables, right?
Yes, sir. We can identify the variables which we can measure using the instruments of
Yeah.
variables.
What's your roll number?
19CH30030.
300
30.
30.
Yes.
Naman.
Yes.
Okay. So there are two ways to get f equal to 0. If you see this one, either we can reduce the number of unknowns or we can increase the number of equations. These are the two answers. Now question is how we can reduce the number of unknown variables? By measurement, by direct measurement. If we measure number of variables, then we can have that information. That means that is known, that is not unknown to us. So by this way, we can reduce the number of unknown variables. You see, it is written here, the 2 points. Specify more number of disturbance variables. Specify more number of disturbance variables. Now you can recall the classification table I mentioned. Disturbance variables are two types. One is measured disturbance, another one is unmeasured disturbance. And at that time I told we can measure the disturbance variables as per our requirement. Now I think you are understanding. You can connect now. I repeat, when we have started the variable classification table, there it is mentioned that the load variable can be classified into two categories, or disturbance variable can be classified into two classes. One is measured disturbance, another one is unmeasured disturbance. And at that time I mentioned that we can go for measurement of the disturbance variable as per the requirement. Now here the requirement is involved. I think you are understanding. Just to know the information of a variable to reduce the number of unknown variables, sometimes or most of the times we need to measure a couple of disturbance variables. In that case, we can say that these are measured disturbance variable. Fine. And second one is include more number of equations. More number of equations where we can get. Basically, these are control equations. More number of equations means mainly these are control equations. Okay. Is this clear?
Yes,
Okay.
sir.
Let us come to discuss this issue with an example system. We'll continue this example system. You draw this schematic, then we'll discuss the degrees of freedom for this process. So you see, this is the liquid tank system. As usual, we are considering Fi as input variable, if not as output variable, or Fo as output variable. A is cross-sectional area, H is height. This state equation or model we have developed before by the application of conservation of mass, and we got this A dH dt equal to Fi minus F naught. So obviously for this particular process, we have only one modeling equation. That's why I have written capital E equal to 1. So far for this example system, we have one modeling equation. Therefore, I have written capital E equal to 1. Student, anyone can tell me what about V? Number of variables?
So
Two.
3.
Three variables. H
3 variables, correct.
left.
What's your roll number?
30018.
Good. There are 3 variables, you see. What are those? Fi,
Fi
height, and F naught. A is not the variable. A is a fixed quantity, so that is a constant, or sometimes we call constant parameter. Okay, so what is your degrees of freedom in this case?
2.
2. Question is now how you can make it 0. Fine. Anyone? Any answer?
So we
So
can
you can
measure the FI and FO so that they will come under the measured load variables.
Which one is load variable?
FI.
Fi is load variable. Do not say F naught. Okay. That means we can only measure Fi. We can only measure Fi. If we measure Fi, then what happens? Our degrees of freedom reduces to 1. You see?
H is our, and then H is our control variable. We can equate it to HSP, and then we'll get one, like one more, like it will become 0 then.
H you can correlate with what you told?
HSP.
HSP. No, it's
We can
control.
correlate F naught and H.
Yes. What's your number?
19CH30029.
Yes. We can correlate controlled variable and manipulated variable. Our controlled variable is height, manipulated variable is F naught. You see, our control objective is to maintain the height at its desired value, that is H suffix SP. Naturally, whenever you are going to discuss the process control of a particular process, I mentioned several times you need to identify the control variable, manipulated variable pair. So it is shown here, you see, H and F naught. Okay, now this is the controller equation. For the timing, you just recall this controller, you note down this controller equation. We'll discuss extensively this equation. Okay, just before starting the controller design, for the timing, you remember this equation. That's it. We'll discuss this equation in details when we'll discuss the controller design. You see these two are correlated, F naught and H. Rest all terms in this equation are constants. Okay, this is the controller equation. I repeat, we'll discuss this controller equation later when we'll study controller design. For the timing, just you note down and remember. F naught is our manipulated variable and H is our controlled variable. Rest all 3 terms are constants. Okay, so FOS basically the steady state value of FO. FOS is the steady state value of FO. Usually we add the suffix S to represent steady state. We add the suffix S to represent steady state. So FOS is basically the steady state value of FO. Naturally, it is constant. Kc is the controller parameter, controller tuning parameter. Kc is the controller tuning parameter. And this is also fixed. This is also constant. This you have to know prior the application, prior to apply this controller equation. And HSP is, I told several times, this you need to fix. You need to set the value for HSP. Right? So this is also known to us. With this, our degrees of freedom becomes 0. You see? And at this point, I want to just mention one thing, that control variable height, for this we can consider either Fi and F0. I think you are understanding which variable we should prefer among F0 and Fi. Clear? I repeat, for this control variable h, so far we have started that the manipulated variable we can choose either Fi or F0. But here, through this example or through this degrees of freedom analysis, you are understanding that we should prefer to Fi or F0.
So why can't we directly measure FO?
Yeah, you can measure that also.
Okay, sir. So then if we measure Fi and FO, then also we'll get F.
Yes. For this small system, it's fine. But for large system, okay, we usually prefer the input variable. But what you told, that is true for this process. We can measure. That's the flow rate, no? So you can employ any flow meter here or here. Okay. Any question? Any other question?
Sir, what are the state variables on which the KC depends?
KC.
Yes, sir.
This KC you were saying?
Yes, sir.
Yeah, this KC basically we determine based on the model. Okay, we'll discuss this issue later. It is somewhat like this. Suppose you have one model equation. We will apply the Laplace transform for that model. Then we will differentiate that equation with respect to Kc. That should be 0. It's an optimization problem. I repeat, you first need to develop the model for a process. Then you find error, that is, say HSP minus H. You keep the error in the left hand side and right hand side all rest of the terms. Then you differentiate that error with reference to Kc. That means d small e divided by d Kc you consider as 0. Then you find the Kc. We'll discuss this tuning part. I think around 15 to 20% of the total course content will goes to this controller tuning only. How to determine Kc and other control parameters. So we'll discuss extensively with different methods. We just wait for few more classes. Anything else? So it is completely specified system. Okay. Now let us come to another example, which is a little complicated system. This is Stara tank system. You draw the schematic of this open loop system. So any difference you are observing between this and the last example, liquid tank system? Any difference?
Yeah, the heating
So
is
we are
also done, so
perfect.
we have to consider the energy conservation.
Correct. What's your roll number?
Sir, 19CH30024.
Yes, this is correct answer. You see, additionally, we have heating part here. In the last example, liquid tank system, there is no heating. Okay, there is no temperature involved. But here we have temperature variable, additional variable. So last example is basically a single variable system, liquid tank system. But this Stara tank heater is a multi-variable system. Okay, because we have more than one variables, state variables I want to mean. Now, in this case, we need to apply two conservation principle. One is conservation of mass and second one is conservation of energy. Can you develop the model now? Carry on. Let me know the two model equations. One is based on conservation of mass, another one is based on conservation of energy. Develop the model and let me know the equations. Borun is there, Borun Balakrishnan, 30036.
Yes, sir.
Oh, you were there. Okay, what is the first equation?
So first equation would be mass balance. So A dH by dt equals Fi minus Fo.
That is same, no?
Yes, sir.
Yes, correct. Ayush is there, Ayush iron, 10072. Ayush iron, 10072. No. Sivay Dixit, 10068. Sivay, 10068. 10062. Udatha Anuradha. Anuradha is there, 10062. Padmasri, 30010. Three double zero one zero Padmasri. 3009 Carnegie. 3009. 3004 Sai Kiran Nayak. 3004. 3001 Abhishek Kumar.
Yes, sir.
Tell me, what is the accumulation term?
In temperature, in energy part.
Yes,
Q,
temperature.
energy input per unit time.
Tell me the expression, mathematical expression for accumulation.
MCP M means AH into rho, CP into T.
Oh, correct. Correct, Abhishek. Rashni Kaur, 10077. So there are so many absent today. 10075. Muhammad Athar, 10075. 30014. Raksi, 30014. 30012. Pratik,
Yes, sir.
You are present.
Yes.
So what is the accumulation term in energy balance?
Sir, so input minus output.
You tell me the mathematical expression for accumulation.
Sir, so it will be like Fi rho Cp.
No. This is input you are saying. I am asking accumulation term which is present in the left hand side.
Okay, sir, one second. So that will be like d by dt of
Hmm.
rho ah
Hmm.
Cp into delta t. That is
Correct.
t minus t ref. Yeah.
Correct, Pratik. Correct. Okay, so in the next class, I will see the modeling equation. Keep the modeling equations ready. Okay, I will ask, I will discuss in the next class. Or if possible, you complete the degrees of freedom analysis for this example. Fine. You develop the model for this Stara tank heater and perform the degrees of analysis. And in the next class, we will discuss this again. Thank you.
Thank you, sir.
Thank you, sir.
Thank you to everyone.